right, so I hope you can all see my screen. So I would like to welcome everybody to today's webinar, What's New in EMS 2021. Our webinar will be given by Dr. Ahmed Khabir, the head of our product development at EMWorks. Without a lot of details and long introductions, I want to just, before we hand it over to Ahmed to talk to us about what's new in EMS 2021, I want to give you a very brief overview of our company. I see that we have a lot of new prospects. Maybe some are not familiar with what we do. So in a nutshell, if we want to talk about what our company does, it's really structured about technology solutions to address your needs and customer needs in general. And if you look at this chart, it's giving you an idea about how these pieces of a puzzle can be molded together to give you solutions to your design needs. So as you can see, the offering technology platform of EMWorks is based on finite element simulation technology. On the top level, you have the electromagnetic. That's really the foundation of the company, high frequency electromagnetic and low frequency electromagnetic FEM simulation in 3D and in 2D. And to those, we add a bunch of other closely connected simulation technologies, namely for structural, for thermal and circuit simulation. And then we have dedicated packages for transmission lines and for electric motors. And all of this technology, what's special about our company is that we bundle all of this into CAD embedded. So we embed these technologies in CAD technology. Namely, our main CAD platforms are SolidWorks and Inventor. Okay. And if we look at it from a product standpoint, well, first of all, these products cover a very wide band of frequency. I hope you see the slide. Looks like the slide is not changing. Okay, so maybe if I go back to, so maybe my colleagues can confirm that we see the, okay. So I'll do it not in presentation mode, because it seems like when we do in presentation mode, demo somehow it's not capturing my screen. So very briefly, so this is what I was talking about in terms of our technology solution, the packaging of our technologies, the high frequency and low frequency finite element technologies, the structural finite element, thermal, circuit, transmission line, and electric motors. And again, the distinctive feature, if I may say for our technology is that it's CAD embedded. Our main CAD embedding is SolidWorks, and we do also offer a few solutions inside Autodesk Inventor. And in terms of how this technology is packaged, well, it's actually packaged in a whole bunch of packages or products, okay, starting with what we call EMS, which covers the low frequency, going all the way to very high frequencies, which is the product we call HFWorks. And in between, we have this Motor Wizard, which is for electric machines, and we have the 2D product, which bridges between low and high frequency. And we have all of these additional optional modules that allow you to essentially have solutions to whatever design you're trying to undertake. So you can mix and match these products really to address your needs. Okay. So today's webinar is essentially focused on our low frequency package, which we call EMS. Okay. And the package comes with a whole bunch of solvers and options and so on. And Dr. Ahmed will be able to tell us a little bit more about this shortly. And so that's what we're going to do today. We're going to talk about EMS and for the low frequency applications, and we'll discover what's new. So in the process, for final couple of notes about the webinar today. So while we have presentation, you feel free to write your questions submit them on the chat, and we'll get to them either as we go along or maybe by the end of today's presentation. So again, thank you for joining us today. And now I'm going to hand it over to my colleague, Dr. Ahmed, to talk about some technical details about what's new in EMS 2021. So Ahmed, I think floor.
I hope you hear me.
Yeah, I think we hear you. Can go ahead.
All right. All right. Very good. Okay, so we have a lot of new features in EMS 2021. I guess time is really passing. Okay. So you can always look in the support in our website, frequently asked questions. Maybe I can put it there. Okay. And actually, we updated the support, the frequently asked questions. Now, before they were mixed together, now we classify them according to the product. There are general questions, and there are questions related to particular products. Okay, and we suggest that you check this page often, because we, update it with including what's new in EMS 2021, and a lot of new stuff, exciting features, and many of you have been waiting for it for a while. And the good news that we have it now, and we're excited to share it with you. So starting with the adoption, and this is the main menu, is the adoption. Of course, many of you have been very patient waiting for this very important feature, because it really makes the life of the engineer or the designer much easier. You don't need to worry about mesh control, even though mesh control, of course, adoption has its price also, because you have to wait longer, right? So as you know, okay, let's start with this three-phase cable. I'm just going to do a simple electrostatic study. Okay, Okay. What's happening? Okay, now, so as usual, okay, you have the analysis types. Okay, now the adoption is available for all solver except transient magnetic solver, because transient magnetic will take a long time if you're going to adapt at each time step. And if you adapt, we just think it's not convenient to do adaptation for transient magnetic, okay? Because it will take a long time. And if you adapt only at one time step, it's not obvious that the mesh is going to be good for different time steps. Okay, so let's just start with electrostatic. Okay, nothing changed. You can do the parameterization, capacitance, the breakdown level. Okay, and now this is what's new, meshing. Okay, now manual right now for this release is default. Okay, and then the next release, the adapter will be the default, because just many of you are used to the manual meshing, so we want to take it in steps with you, so till you get accustomed to the adaptation. So the adaptive, okay, so the adaptive, all of the solvers, all of the analysis types, it looks the same. Okay, so this is the maximum error. This is the energy error from one pass to another. Okay, how much? Of course, relative error. This is a percentage. Okay, so this one is like 0.1%. Okay, and this is the default value. If you want it to do faster, of course, you are willing to accept only 1% error. You can change that. But of course, the smaller the error, the longer you have to wait, because it will generate a lot more elements if you put a very, very small error. Okay. For the electrostatic, the default is 0.1%. For magnetostatic, I think AC magnetic is 1%. And so electric conduction is 0.1%. So it depends on the analysis type. You're going to have different error level. Okay, this is maximum adaptive passes. We think that really if it reaches 30 and it does not converge, you know, we think that's probably not, probably is going to generate a lot of elements for the maximum adaptive passes. At least from our experience, it could reach 30, you know, some problems, but anyway, you can increase this number, okay? But, you know, more than 30 is probably going to take too long and generate too many elements, okay? This minimum adaptive passes, because sometimes if the mesh is very coarse and then it's not accurate, then the energy is going to converge very quickly and give you false positive, you know, that you think that convert. But so we want to at least do 2 passes minimum. And this is also important. Okay, suppose it converges at pass 5. Okay, the minimum convergence passes means that we want to wait for 2 consecutive passes to converge. For instance, if it converges at pass 5, it reaches the level of say 1%, and at pass 6 it goes above 1%. Then we don't think it's just a local minimum. So we want to make sure that it converges. So we want to make sure, like say 6, 7, 8, 9, 2 consecutive passes. They have to have this error. Again, for electrostatic, the default is 2. And it can vary from one analysis to another. You can change this. You can make it 3, 4. Okay, but again, the larger this number, the longer I have to wait. Okay. So what is this 30%? All right. So, of course, in each pass, we're not going to refine 100% of the elements, right? Because then it defeats the purpose of adaptation, right? So it means the first 30% or the 30% that have the largest error, okay, they're going to be refined. Refine, okay, means is going to be the element going to be divided to other elements. Okay, of course you can make this one smaller or larger. So I just wanted to take time in this example to show you this adaptation part, okay? Because it's going to be the same for all of them, okay? Then you say, and if you change and you're unsure about that, you can always reset, okay? And you say, okay. Now the mesh control is still there. You can still apply mesh control, but we don't recommend that you apply the mesh control. That's the whole purpose of the adaptation is you don't worry about the meshing, okay? It's just ask it to mesh and it should do it. It should follow the gradient of the field, okay? Where there is more error, okay, it's going to do a final mesh. So let's look at the initial mesh. This is my initial mesh, okay? And now if my adaptive mesh is good, it better follow the gradient or the where there is too much change in the field, or there is largest field or largest change in the field. So this is my last adaptive mesh, okay? Now I can look at details, okay? It gives me the number of elements. The initial mesh is 19,746. Less adaptive mesh is 338,930. Okay, closed. So this is my adapted mesh, And if I want to look at the convergence data, okay, this is my energy. This is the convergence data, okay? So this how it went from, okay? It took 6 passes to fully converge, okay? All right, so now, how do I know this is correct? Well, let's look at the electric field. Look, well, let me look, do a new plot. Okay, so this is my electric field plot. Now, if I want to overlay it with the mesh, okay, there you go. See, I know that this is a good adaptation because you see, my small elements, the adaptation is really around the large field, large gradient or large field. Okay? And that is the nice thing about the adaptation. It really adapts where it's needed. Okay, and this one clearly demonstrates that it did the job. Okay. All right. So that's my electric field. Once it adapts, everything else is the same. You know, your solution is you can look at the regular stuff, the electric field, the safety factor. By the way, the safety factor of this guy is really, this one is going to break down because it exceeded 1.2, by the way. Okay. Now, the rest is the same. Okay. One new feature that we also added next to the addition to the adaptation is a streamline. Okay, the streamline, you can do it for the electric field or magnetic field. I'm going to show it later on in some. This is my streamline. This is my electric field lines. Okay, so I can. These are some controls. Can display here. Well, it's too much, too thick. Okay, I can change it. I can change. This is the width of the line, the concentration, you can change it, okay? Can change, so we have a lot of control. You can change your streamline. I understand it's not very probably relevant in the case of the electric field, but it's very relevant when you look at the magnetic flux lines. Usually people want to see the streamlines, okay? The rest is as usual. So this is new. This is new feature, streamlines. Okay. All right. So let me close this one and show you another example. Okay. Don't save. Doesn't matter. Show you another example with also adaptation, rotational actuator. What happened? Rotation actuator. Okay. All right. Let's look at this. So let's look at the. I'm going to hide the coils. Just going to see where is. This is my initial mesh. Okay. And now this is my adapted mesh. You see, now, okay, let's see, is it good or not? Again, is by looking at the flux density. You see, it really meshed, you know, around the high field regions. Okay. Now, you may ask why I have very fine mesh around the rotor. Okay. Well, we also added a feature. If you ask, this is torque, this is my torque, okay, around the axis. Because I have, let me hide the mesh. Because I have virtual work, I want to compute the torque. And you know the torque is the most difficult quantity to compute. Usually we recommend that you do a very fine mesh. If you want to compute the torque, say, look, please, on the surface of that body, do a very fine mesh, because the torque is very sensitive to the mesh. The good news is now we do it automatically. Just say I want to compute the torque or the force for that matter. Okay, you say I just want to say that you want to compute the torque or force on that board, and we automatically, after it converges, we go another pass and we do for you automatically do a very fine mesh on that body. So we assure that you have an accurate value for the force and torque. Okay. All right. Now let me look at so this is the Streamline. Okay. For this showing the magnetic flux density. Okay. You can again play with the parameters. You can make coarser, denser, and you can play with the thickness of the line. Okay. So again, the Streamline is available right now in all analysis types. Okay, and okay. So this is the adaptation, and again, the adaptation, you can do the same steps as I showed you earlier. Now everything else, it remains the same, right? Once it converges, okay. And usually, if you look at this, this is I think one of the problems that we use it for in the tutorial. We actually ask you to recommend that you do a fine mesh. Okay, a mesh control, and as you can see, now we don't need to worry about that. And this is really a milestone that we're really very happy that we eventually have it for you, and it's going to facilitate your work and your design. Okay. Next, let me see my list of features. I have the wait. Okay. Before we did not have transient magnetic with the circuits right now. Okay, electric and electronic circuits. We had transient magnetic, but we didn't have the circuit. Right now, we are happy to tell you that now you can mix transient circuit elements, not only with circuit elements, with nonlinear circuit elements like diodes and like diodes, okay, and switches. So this is an inverter. Okay. This is a simple the model. Okay, this is a simple transformer, right? Primary, secondary, and this is the core. So for coupling the circuits, I'm sure all of you know, we actually just want to show it to you the properties. When you do coupling, okay, you're going to choose coupling to circuit, right? So, and then there's no need for, because this is not a tutorial that I'm just going to go over the features very quickly, okay? If you needed more in-depth questions, or you have one particular feature that you want us to cover, we will be happy to schedule with you a one-to-one meeting to show you how to, for instance, if you're not familiar how to use the coupling to circuit, how to use the circuit editor, we'll be glad to do that. So this is an inverter. You have switches, and diodes and a voltage source, okay, and primary and secondary. So in addition to this, now let's look at the results, okay, with the inverter. I'm going to put this in this. Let's look at the current. And now, those of you familiar with the inverter, you know that this is an inverter currents. Okay, it's nicely follows and it's very accurate. Okay, and this is diodes uh, the induced voltage. And again, let's add plot, and you know that it's the induced voltage. The rest of the stuff is as usual, right? So you have all the good stuff, the current, the voltage, the leakage, everything as you know, solid loss. I don't think I have solid loss here. Yeah, for this one, I don't have any solid loss, okay? So, okay, now, so this is the feature of coupling to transient magnetic with circuit coupling and diodes and block switches. And this is, again, this is a brand new feature that we just added. Another feature, I'm going to still show it in the same model, is AC magnetic with circuit coupling and thermal. Before we didn't have this, now we have it. Okay, so if I look here, this is a full bridge. Okay, I don't have any switches in this case, but I have diodes, nonlinear elements, and this is what is called a full bridge. Okay, and as you can see, the full bridge is the current is gonna look very different from the inverter current. Okay, and there you go. This is a full bridge current. Okay. Same thing, the rest of the quantities, you can plot them, okay? In addition to circuit, now we have coupling to thermal. And if I look, as you know, my thermal results, and again, I don't want to repeat myself, if any of you, because I have to go fast over the features, okay? So it's not meant to be a step-by-step tutorial or one particular feature, it's an overall presentation, okay? So if you want one particular feature, how do I couple to thermal? How do I add a circuit element? How to do this, how to do that? Please just let us know, and we will be more than happy to do a custom presentation for you for a particular question. So the thermal, as you know, once I have to, and this is a nice thing about this EMS, right? Because you have everything integrated, right? You have electromagnetic input, thermal input, and everything in the same tree. You don't have to, and the whole idea of our company is integrated software, is CAD integrated, thermal integrated, structure integrated, circuit integrated, everything is integrated. You don't need to import, you don't need to export, no mess. Okay, so this is nice thing that, so we have the electromagnetic input and the thermal input, of course, and thermal input. Again, you can do all of this boundary condition to the thermal. And again, this is not meant to show you how to do thermal, but so mixing them, the thermal results, I can look at my temperature, okay? And this one, I can now animate my temperature, okay? While there are so many steps, so it's going to start animating in 1 minute, okay? There you go. Okay. So if you don't want to animate, if you want just plotting thermal results, say step 1, okay? And if you want just in the core, just click on the core, okay? And then this one, this is step 2, okay? This is step 3, step 4, step 5, and you keep changing, okay? So coupling AC magnetic with circuit elements and thermal. This is what it is. It's done. Okay. Now, another feature that we added, you don't need to save, is transient magnetic with motion and thermal. Okay, so let's get that. For that, I'm going to use this this one here. This is a braking system, ventilating braking system. It's a little bit large. Okay. So this guy has motion. Give me a second because it's a large problem. It's opening. All right. So this, as you can see in my properties, I have coupling analysis. There's thermal coupling and motion coupling. We didn't have this before. We had only motion without thermal, but now you can mix motion and thermal. Furthermore, and we know that the time constant for heat and electromagnetics are very different, right? I mean, in EM, we talk about 10 to minus 3, it's in milliseconds, and in thermal, we're talking about seconds, minutes, or even hours sometimes. So that was one of the difficulties, is how to mix different physics right in the same interface. Because again, we didn't want to create just a thermal solver where you export your data and do a thermal study. We want always, our philosophy, our company, is to have everything integrated in one same environment. That's why it took a while to develop this feature, but now we have it. So if you want to show you the, I can animate. Okay, so this, you're going to see a motion here. It's animating the magnetic flux density, and there you go. So the brakes, the discs are moving, right? So you want to apply a current in the coil that's supposed to stop them. Okay. Okay. So now, okay. So once, as you can see here now, this is a nice thing now. This is a nice feature. Okay. Continue Thermorun. So once you finish this case, if I open my results table as usual, right? Show my results table. My results table, okay, it goes to 33 milliseconds. Okay, and of course you can, as usual, you can plot all the goodies, you know, all the quantities, in the table, the torus, currents, inductance, flux linkage, solid loss, you know, like let's say, let's just break, you know, just for the presentation, this one is showing the solid loss. Okay, if you want to plot the torque, okay, and as you can see, of course, this is a typical of a braking system. Eventually, the torque, you know, converges; it becomes a constant. Right. So, what's fast about this? You may ask. Okay, here it is. Once I finish the electromagnetic, I say around to 33 milliseconds, and I want to go to additional thermal time. That's where we added. Okay, for the thermal, it is not 33, but actually I ran it from 33 milliseconds to 600 seconds. But if you want beyond that, you can say go from 610 or if you want more time, you put more time. If you want in the thermal, just click and run. It's not going to solve, and this is important. Okay, it's not going to solve and waste your time doing the electromagnetic. Okay, it's going to pick from where it stopped and going to do the thermal solution. Okay, so you can reach steady state. Think, if I'm not mistaken, looking at thermal results, I think this is my okay. If I want to animate, okay. Okay, oh, this one is because it's looking at the, but I can look at the, you can look at the, see here, 371 seconds. Okay, can change it. Okay. So the thermal result, when you display or animate your thermal results, they're going to have a different time from the electromagnetics. And this we are really proud of this, that we are able to give you something, a solution that can, it mixes the time constant of the electromagnetics and the thermal, yet in the same integrated environment. You know, it's just a different folder. You'll be able to look at different physics, you know, in the same environment, you know, as you expect from us. Okay, that's second. Another feature is, I said, the mixing. Okay, you also have steady state thermal for transient magnetic with or without motion. I think I showed you this one, okay? But let me see. Probably have some other example I can show you. Okay. Close. Okay. The other example that I wanted to show you, this one. This is a three-phase transformer. That's the problem with the large modules. They're more impressive, but they take more time to open. Okay. Just bear with me, it's coming. So this one, yeah. So this one is an AC magnetic with steady state thermal. Okay. This is another feature, and with coupling to circuits. Okay. So I think I showed you the other transformer, but if you wanted to see something more, so this is your flux. Okay. And again, you can always, if you want to look at only at the core, which is more relevant, you can look at the flux only in the core. Okay. And again, you can animate. So this one has the, this is your circuit. Okay. Because you have 6 coils. Okay. And again, you can look at your temperature. Okay. So this mixing the AC magnetic circuits and steady state thermal. You can also do transient thermal. Okay. So that's, let me see. Yeah, there is another feature that I wanted to show you is this one. We turn the eddy current off, right? But one feature that we added is you can turn on and off eddy currents if it is a metal. and for the AC magnetic and transient magnetic. Okay, if you have eddy currents, if you don't need to worry about eddy currents, okay, then leave it off, because it's going to take a lot more time, okay, to solve for the eddy currents. You're going to have a lot, because in the T omega technique, you have what is called the T vector, and the T vector is going to give you a lot more unknowns or degrees of freedom. Of course, if you need it, you turn it on. That means in this part, it supports eddy currents. Okay? If it supports eddy currents, okay, you choose. It depends on your application. Okay. If eddy current is important to you, you turn it on. But we made it very easy for you. It's just, okay, I don't want eddy current, come back here, turn off eddy current. Okay. There is also the continue adaptation run. Okay. Let me, so this is the AC steady state thermal and eddy currents. Okay. Let me see if I go back, close this one, don't say. Okay. If I go back to cable, where I have the adaptation, where's my file? Okay. So this one, it did, as we should saw earlier, convert. Okay. So if I make a copy of this one, okay, study 2. Okay. Now I already have, if I already have an adapted mesh, a converted mesh, but if you want to continue the adaptation run, okay, I can simply, because it did copy my mesh. If I run it right now, I have an option to either revert to initial mesh, okay, or if I continue run, what it's going to do, it's going to start from that mesh and add whatever you requested. So if back here, my meshing, if I asked it for more conversions, of course, I mean, if the error is the same, it's probably going to do one more pass to convert. But if you change the error, okay, it will start from that mesh and give you more passes. So you can copy an entire study and keep the start from that mesh. Okay. So we did the continued transit thermal, AC magnetic, eddy current. We also added in the options, okay, in the mesh control, in the options, before we had only the manual, right? In EMS options, you have the default values for the adaptation. Okay, so if you want to change your default values, you can change them right here. The percentage, what I showed you earlier, you can change them. And we added some more options. Okay, adapt initial. Sometimes if you have if you have a parametric study and you want to only have first scenario adapted, and they use that mesh for next scenarios, you can choose that right here, adapt initial scenario only. And also, if you have motion with magnetostatic or AC magnetic, again, as I said earlier, for the transient magnetic, we don't have adaptations, but you can still have motion with the other solvers like electrostatic, AC, and magnetostatic. You can also ask to adapt only the first motion step. Okay, so we have more options here. Okay, so that's okay. The other feature that we have in your you go EMOX in the demo viewer, and this is a nice thing, right? So in the demo viewer, like in my case here, if there are new models available, okay, as soon as you open the demo viewer, it tells you there are new models available to download. Okay, so you can click and download them. And we added more, by the way, added more value, more models, examples in the demo viewer. It's richer right now. You have more examples. You can download the. Okay. There are other features that in the this one is electrostatic. Let me close this one and open something that has magnetic stuff. Wherever this one or okay. You can now, and of course, thank you very much, many of you, because of your comments and suggestions, we keep improving our software. So now you can change the filling factor. As you change the filling factor, it automatically right now, if I don't like that filling factor, change this 1.5, okay, it automatically updates the AWG. We didn't have this before, but now we have it. Okay. I think, yeah, we have also the solver. We have it's internal. You don't see it, but we have the what is called patch C. Patch C solver. Right now, it's the iterative solver. When you go to options, properties, and the advanced analysis, the advanced properties, the multi-core iterative solver, okay? We have right now internally, it's faster than before because we are using the patch C, which is coming hopefully in the next release. Using patch C, you'll be able to do, if you have a cluster of parallel machines, and cloud is hopefully before the end of the year, we're going to have that feature. But right now, we're using from the patch C only the acceleration. So the iterative solver right now is faster than before. Okay. The GPU also coming. Hopefully, we already have started testing it locally. It's going to come hopefully in the next release. And we have always, as we expect from us, keep improving, and a lot of improvement came because of you, the user. You demanded from us, and you expect from us always better and better quality and more features, and we are committed to that. We'll be happy to answer questions. If you have any questions, either now or you can submit it later. We'll be happy to answer your questions. And if you have one particular feature that you want us to implement, we will put it in our list of features to add. Okay. We are a dynamic company. We are small but dynamic, that we work very closely with our customers and to make it really easier and more powerful for you, the user. Okay, I think that's it. Don't have any more. I don't want to take much more of your time. It's almost 54 minutes right now. So again, thank you very much for coming, and looking forward to hearing from you. If you have questions or requests for improvement or features or so on and so forth. Okay, thank you. Back to you, Amar.
Yeah, so thank you, Dr. Khabir, for that presentation. I hope you've seen that there is product is evolving and so on. And I just wanted to mention to those of you who are on maintenance and they have access to the software, obviously you can keep track of this all new features in the what's new section in the software. And by all means, like Dr. Ahmed said, if you have questions now or later, we'd be happy to answer them, and keep your features and requests coming so that we make the product even more appealing and meets your needs. So maybe take a minute or two if there are any last minute questions to be asked. Yeah, I see there is a question about adaptation. Are you able to mix mesh controls and adaptation?
Yes.
Okay.
The answer is yes. Yeah,
so maybe elaborating on that is basically I think that's we get. So I think the idea is basically to elaborate is that mesh controls can help you possibly maybe shave off few iterations from the adaptive number of passes. So if you know a priori where the mesh is going to need more elements, mesh controls may accelerate the convergence process. I think that's what the question was alluding to.
Why I don't see the question, Amar? Hello, Amar, can you hear me?
Yeah, I can hear you. Maybe because
I don't see the question.
Yeah, maybe.
Any other questions? So yes. So the answer is yes. You can mix.
Okay. So okay. Any additional questions in the chat box? There is a question about, can you elaborate about the multi-core and GPU support? I think there is a question.
Okay, so the multi-core, we are working on this new version. It's going to come released before the end of the year, where you will be able to submit your job to the cloud. If you have whether Microsoft Azure, I think we're going to start with Microsoft Azure, okay, where if you want to from the EMS, you'll be able to submit your job. If you have a very large problem, you can submit it on the cloud using available, so you can use maybe, I don't know, thousands of CPUs, okay, and GPUs. The GPU also is coming, and both the GPU and CPU will be available, so you can submit your job to the cloud. So kind of cloud computing, as they call it. We are adding currently such feature to our software. We already did preliminary testing, and the GPU, if you have a lot of GPU cores, it's really fast. It's much faster than CPUs. Even on a small machine like a laptop that I'm using, the GPU is really faster. But again, that's really in the testing. It's going to come hopefully in the next release.
Okay, very good. So as you can see, there are more exciting things coming. And I see one last question, but maybe I'll take this one because it's talking about the pricing and the access. So the cloud is obviously is going to be connected to your desktop version. Okay, and the way it's going to work is that you'll be able to, on top of, you have your regular purchase, and you can opt into cloud credits to use them, to leverage cloud support for your needs. Okay, for GPU, it's going to be a high performance option. It's going to be an optional module that you can add to your existing, but GPU support is not accessible through standard maintenance. It's a new additional feature. All right. I don't see any more questions, so I think we're gonna. It's been 1 hour, so thank you all again for attending, and we look forward to your continued feedback and requests. So have a good afternoon and a good rest of the day wherever you are. Thank you.